Oh, there we are. Cat Kate redeemed. The random physics fact. I don't have anything recorded for that. That's just, yeah. But we do normally zoom in. Right, what I normally say at this point, that's what CatKit knows, is that, the last few times I've done the random physics fact, I have whipped out a copy of Physics World and asked you to choose between page 1 and 67 or whatever. So tonight, as a special treat, because it is a celebration of 10 years since I submitted my PhD thesis, and I said it's 248 pages. So, ignoring the front cover, because the front cover is literally, I mean, it's page 1, and there's a blank page 2. Then there's a nice quote on page 3, but that's not it's traditional on a thesis to put like an inspiring quote. So that's not a physics fact, and that's in the preface anyway, so it doesn't count as a page number. Right, so page numbers start from after the contents page. Let's have a look. List of thanks, list of tables. Yeah, there's loads of preamble. There's like 20 odd pages of preamble. That's just what you have to do. Chapter 1. There we go. There's chapter 1. Hang on. I've skipped past it. Chapter 1 starts on page 1, and then the official main body of the thesis finishes on. Okay, so it's not 200. It's 248 physical pages in the document, but it's 186 pages of stuff. So a number between 1 and 186, allowing me some time to work out where that is, because it's offset from the actual page number in the document, if that makes any sense at all. Possibly not. Cat gets your choice. It's your redeem. 123. Right, so that's going to be... I'll type 123 in, but it's not going to actually be 123, if that makes sense, because... Ooh. Right, flickered then. Yeah, 123 is 81, so quick bit of mental maths. We need to add 42. Oh, a minute in her life. Yeah, I need to add 42 onto that number. So it's 123 plus 42, 165. Is that right? There we go. Right, so. No, you're not losing your eyesight. Don't worry, I did it deliberately. Because there are some figures in the document that are possibly still commercially sensitive. I'm not sure. I was okay to publish them in the thesis, but I just wanted to make sure I wasn't just brought... I mean, nobody'd really know. Nobody'd notice. But still, I'm a professional. I pride myself on being professional. Damage limitation, not really needed, because who's seen it apart from us, right? Apart from us little cozy group here, but still. Better safe than sorry. You never know who could wander onto the stream and just like, oh, and then they suddenly manage to build a product. No, I don't think it's going to happen. I don't think people are watching my stream to work out how to build lasers, but anyway. What's this saying? Full spatiotemporal models. Yeah. I mean, this hasn't worked out very well. This is just a wall of text. Where do I even start? Well, maybe I start by reading it. Figures 5.13 and 5.14. It's 14, isn't it? No, it is 13 and 14. You should always say the numbers after a decimal point in maths individually, but in this case, it is figure 5.13. That's correct, because it's the 13th figure of chapter 5. Figures 5.13 and 5.14 compare the results of the full spatiotemporal models to the experimental data in figure 5.4. The accuracy of the temporal pulse shaping model described in section 4.3 is expected to decrease at large delta t, since the frog measurements, sections 2.2.2, are known only over a finite t range. The central 40 femtoseconds of the data in figure 5.4 has therefore been selected, roughly corresponding to the overlap between the highest intensity parts of the pulse envelopes in each of the interferometer arms, section 4.3. There you go. Hope you're happy with your random physics fact there. The central 40 femtoseconds of my data roughly corresponded to the overlap in the highest intensity parts of the... Yeah. Didn't work. But what I can tell you about, let's see if I can find a page on Frog. It's an acronym. And somebody actually at a conference. I am indeed, says Catget. You are what? What? Wikipedia obviously is you know, is the place to go, surely, right? So somebody at a conference asked me, that was their question after I did the whole presentation. They said, "What is frog? Or what is a frog?" And I just assumed naively that Cat happy with. I'm happy with my random physics fact. Frog can be the proper fact. Because that is really clever and really interesting. I don't know if I can explain it very well. I'm going to need my whiteboard, aren't I? So, well, if the article is good enough at explaining it. But anyway, yeah. Even in this expert audience, there was somebody who didn't know what a frog was. So, a frog in short, as I say, it stands for frequency resolved optical gating. I could say it again. Used to be able to say it when I was doing the PhD. And it's a way of measuring. It says a general method for measuring the spectral phase of ultrashort laser pulses. What it is a very, very clever way using an interferometer. I'm going to have to explain that as well. Interference. Yes. Look up interference patterns. Look at double slit experiment. That's to explain all of that is a physics course in itself. But yeah. All right. The basic idea of interference is that if you've got two coherent light waves and you overlap them, you get interference between the two beams, and you can get interference fringes and interference patterns and stuff. That's not really making it any clearer. Well, ripples in a pond is the answer, I suppose. I mean, right, okay. Interference of ripples in a pond simulation. This was actually teaching. That's what we do. Yeah. There's an A-level physics video. That'll do. That'll do it. Let's mute it though. Oh. I think I just heard that in my headphones. But there we are. You got waves coming out from a source. They're talking about a speaker there. Same thing happens with sound waves as with light waves. You've got two sources next to each other with waves of the same frequency, and then where they overlap, you end up with well, they're doing a double slit experiment with an actual speaker or a microwave generator, maybe. I don't know. No, it's an actual speaker. That's very neat. I like that. And you get this sort of effect, right? You get bits of the wave where they interfere constructively, so the peaks of the waves line up, and that gives you like a double height peak. And then you get bits in between where the peaks of the waves, the peaks of the wave from one source overlap with the troughs in the wave, the bottoms of the wave in the other one, and when you get the top and the bottom adding together perfectly, they cancel out. Because it's like plus a bit, minus a bit, cancel out. Yeah? Sort of, roughly. That's a real whistle-stop tour of interference. So what you can do is use that interference in a very clever way in a crystal. You pass two laser beams through each other in a crystal, and where they interfere, you get bright spots. But what the clever thing about frog is that there's a way of doing it. There's a way of setting it up so that it sort of interferes in two different dimensions, and that's I've not entirely made that clear because I mean, well, that's the formula for it. I mean, there we go. Let's have a look. I mean, if you can understand that, then yeah. I'd have to work out how to explain that to explain it properly to you. But you've got two dimensions basically. Let's see if we can do that. We can open the whiteboard up quickly enough. Ooh. No, that's not quite worked, is it? It's not opened the app. It's just made that bigger. Hang on, right. Okay, whoa now. Right. And let's plug this in. So I've almost got this working earlier. Yeah, cool. Right. So, you've got a sort of grid in two dimensions, and you get a pattern that looks a little bit like a frog. I mean, this is me drawing it from memory. I remember it sort of looking a bit like that. And all this would be filled in. That's not meant to be a really terrible drawing of an Apple logo. That's what you sort of get on the screen, right? And it's in 2 dimensions, and we don't do anything with that. The computer program sorts it all itself. So this is like an image of the 2 laser beams going into some sort of crystal. There's the actual crystal. Let's say there's a camera looking at the crystal, and the 2 laser beams go into it like that. Yeah. I don't know. It's a really sloppy drawing of it, and where they interfere, it creates this 2-dimensional, odd-looking pattern. But then a computer program runs and works out. It does some simulations of what the laser beam is doing, and it produces. This is why I think it is really clever. It's like I say, I don't understand what that frog trace means. I just know what's causing it. The computer program that comes with the frog device is what does all the work for us, as I say. And it then simulates 2 laser beams crossing in a simulated crystal, produces that frog trace. Oop, wrong button. produces that frog trace, and then it matches the experimental one with the theoretical one that it's just made as I should say simulated. Matches the experiment with the simulated, and it goes, right, are they similar? Maybe a little bit, and then it does another one. And it changes the laser beam parameter slightly. And it does it again and again and again until it gets closer and closer to the actual experimental trace that you see on the screen. And then it goes, right, this matches. That must mean that the laser pulse is this long, because ultimately it's a way of measuring how long the pulse is. You can't just take out a stopwatch because, I mean, it's the speed of light and all. There's that. There's that on top of everything else. But also, these are ultra short pulses, so even the fastest measurements, we're talking femtoseconds here. So, actually, yeah, let's go back there. So you, as I'm sure you know, no. No, I need to turn off the pen. Hang on, right, okay. Move that up there. So you've got seconds, and if you ever used a stopwatch, you've got milliseconds, right? So a millisecond is 1,000th of a second, and then you've got microseconds, which are 1,000th again, and then you've got nanoseconds, which I'm sure you've heard of. They're 1,000th again. So each time we go down a step, we're going down 1,000, right? Go down a factor of 1,000, I should say. Not going down 1,000, going down a factor of 1,000. Then you've got picoseconds after nanoseconds. I'm not just going pss on the screen there. Picoseconds. And then finally at the bottom, you've got femtoseconds. So if you divide by 1,000, divide by 1,000, divide by 1,000, divide by 1,000, you can imagine how small a femtosecond is. And electronics work in nanoseconds. Your computer is operating at a level of, like, processes are happening on the nanosecond timescale. You can get devices that measure picoseconds, but yeah, it's starting to get difficult, right? And by the time you get to femtoseconds, your laser pulse is so short that the only thing that you've really got available to you to measure the length of the laser pulse is the laser pulse itself. That's why you that was almost a coherent that was almost a coherent explanation. That's why you need to overlap the 2 laser pulses in the frog, because literally that's the whole purpose of the frog. The whole notion behind it is it's okay, it's just an update. Nothing's come unplugged. We're okay. So yeah, you use the laser pulse itself to measure itself in this very clever way, which I won't explain again because I've already gone over it in too much detail. I don't mind. I just mean I've probably bored you to death now, but you use the laser pulse itself to measure the laser pulse, because the laser pulse is the only thing short enough to measure the laser pulse, because we're working with, I think, 30 femtosecond laser pulses. They're extremely short. Extremely short. Shorter than anything could measure. Basically, anything electronic that could measure the start of the pulse would never be able to react in time to measure the end of the pulse. Think me reacting in Apex Legends. That's what any normal electronic device would be like, measuring this laser pulse. It's so short. It's also really intense, but that's another topic. That'll need another redeem. Roop, hello, and Sarah, welcome back. Jamie, every time I come to your streams, I'm fascinated by what you have to say, even if I don't often understand. It's okay. I'm stopping there. I'm closing the whiteboard program now. But we did have a random physics fact redeem because it is my 10th anniversary of. I always debate this: is it the 10th anniversary or is it the 9th anniversary? Because it's technically, I suppose it's the 9th birthday of submitting my thesis, so it's the 10th anniversary, maybe. I don't know. I always worry about that far too much. But it's 10 years since I put a 248-page document into the uni for assessment